Alright, welcome to a new video where I want to talk about separation axioms and, the properties of, connectedness and compactness. I'm going to cover, of course, separation axioms and countability axioms first. I want to go over the separation axioms first. So, separation axioms. It's worrying. Separation axioms. The first one, which is called T. Well, I don't want to say this because it's not really right, but I'm just gonna say it. Let's just say T1, I'm just gonna say the first of the ones we're considering. They're more. Pretty sure it's T0, so this isn't technically the first. Don't care. We're going with T1 first. Because I don't think it's any use to discuss anything from that's not in T1 through T4 until later. And at that point, it's like T2.5, T3.5. So T1, we say for some x and y within some topological space X, there exists an open set so that X is within this open set U. Oh my god, this died. It was working just fine. But Y is not within. Oh my, I missed completely. Not within U. So in other words, first you can pretty much make it out what it's supposed to mean. That's T1, right? T2 has actually its own name. T2, it's called Hausdorff. And it's one of the more important ones we're going to talk about. Of course, there's more important ones. Well, not separation axioms necessarily, but other stuff. It's going to be more important or less important depending on what we're doing. T2 Hausdorff. So for any x, y within x, within a topological space X, there exists, open sets X within U, Y within V, so that their intersection is disjoint. Oh my, that's so. It's not bad, I guess. Just looks a little weird. It's not a line through. It's not zero. It's really nothing. That's T2. Now T3, T4. These are the ones that I don't particularly like much because they're not really fun at that point. I guess I had to talk about them. So T3. Oh my. Okay, so T3. T3 spaces are so that, oh my god, for some closed sets. I don't know. I'm just gonna use. I don't know what letters I can use. Let's just A and B. I say why not? There exists open sets a subset of within, let's say U, be a subset of V, so that U, V disjoint intersection. T4 is a little bit different. We're going to use a new term. Say T1 and normal. I think it's the term we use, normal. I'm thinking about group theory now. It gets me remembering weird. Meaning, essentially, normal. I want to talk about normal. Normal meaning, of course, a point X and a closed set. They have, well, whereas there exists open sets X within U, closed set V. I don't like to be pretty clear. I'll use A again. A is subset of V. Of course, I'm not going to put the equal sign below it because, you know, if they're equal, I don't. Okay. The situation, of course, where you can be both open and closed, but I'm just going to pretend it doesn't exist for now. But honestly, it shouldn't really matter. I'll just put there. Why? Because just be safe, I guess. Let's know why. Reset again. U, V, disjoint, intersection. Very much like this. Actually, something you might have noticed, of course, is that like something like T1 implies T2 implies T1, T3 implies T2, and you know. So you can actually sum this up in one quick thing. So we just say Tn implies Tn minus 1. And of course, this is a separation axiom. So a T2 space, a Hausdorff space, is on the side of the T2 axiom. And then so it implies T1, or just a T1 space, so the T1 axiom. T4 gets me weird. It's weird. Countability axioms. Axioms. Lovely times. There's only 2 actually, which is nice. They're not anything special either. They're actually pretty good. So don't think we have a specific letter for them. We just say first countable, second countable. First countable. A first countable space is essentially a space so that for all, you know, X within the topological space X, they're countable neighborhoods of X. Neighborhoods of X. Oh my, this is actually giving up. Second countable is way more basic, even more basic. Countable. Okay, a set of countable space is just a space with a countable basis. So I'll just literally just say countable basis. Countable basis. Fun. something you actually can note here, if you look at this, you might notice something fun about it. And that's that metric spaces actually satisfy this. They're both first and second countable. So the first and second countable. It's actually something you can look at, like, how do you prove this if you really want to? But it's, I mean, if you look at it and think for a minute, you should be able to make out the idea why, right? Of course, if you want me to explain, I'll just say it. But you can say that in the comments or something if you really need me to explain. But otherwise, we are done with this painful part. We're on to the fun part. Fun being a pretty subjective term here because we're going to connected and compact spaces. I want to talk about compact spaces even though I kind of looked them out on the notes. I looked at them before recording this. I left them out. I'm gonna add them in later, but they're not in there right now. But I'll just talk them first because honestly, connected spaces are probably going to end off on. So, a compact space. Well, actually, I need to talk about open coverings. Well, coverings in general, but I'll just talk about open coverings. So, oh my god, this thing's... Okay, I'll just... fucking, you know. I don't even work my finger. Covering. A covering of a space is a collection of subsets. I'll just say collection. I'll just say yeah, collection of subsets. We say A within some, I'll say fancy math counts, you know, even though I'm not really doing that right now, but I don't really care. I'm gonna see A, of course, I'm assuming proper subset of a topological space X, so that the union of all A within this C is X itself. That's a covering. An open covering would be open sets. And, you know, I mean, if you're a closed covering, that's kind of weird, but I don't think you really do a closed covering. You could, but no. Now they're compact. So compact spaces are spaces that, every open covering has a finite subcovering, right? That, I mean, yeah. That's just I think you can guess what subcovering means. Just take it. Has an open subcovering. Oh, it's actually dying. Okay. I didn't expect it. It's working just fine. Then we have the QED thing left. Oh. See it. Covering. This is what it means to be compact. Every open covering, has an open subcovering. Yeah. It would be subcover. That's right. Alright, so now the final thing we're gonna, well, not really final, it's just giant. There's a lot of stuff in connectedness. We're gonna cover three things in connectedness, which is just gonna be normal connectedness, path connectedness, and being simply path connected, which is actually a pretty good one, because it kind of lets you think, it kind of starts you off thinking about homotopy. But I don't really care much, so I'm probably not gonna go into depth with that until I do anything with algebra topology, which will probably be not a while, because I also want to cover algebra on the channel. But just say I upload it once a month, it's not going to happen very soon. So a space is connected. Oh, I may have to please work. Well, disappointing. Oh no, we're going for connect spaces. I can see my terrible handwriting. A space is connected if there is no partition, right? You know what a partition is? It's just a collection of two or more sets that are disjoint, and their union is that set, which is of course being partitioned. That's what I mean. That's what a partition is. So that means you can't really, split it into disjoint pieces. That's what it means to be connected. Now, path connectedness requires another definition, and that is that of a path. A path, we say a map from the unit interval to a map to a point is map from one point to the next. So let's see this x. Say a map from points from point A to B. Is a path if versus path is of course from A to B again. If 0 A f of 1 is equal to B. Of course, I mean, if you think that intuitively, it makes sense, right? You're just moving it along a path, moving this point from a path to another point. You can think of this like, the in-between, or like time, if you really want to think about it like time. Now, path connected. A path connected is, I think it's let's talk about a path component first, actually. I'm pretty sure. Yeah, I do. Path component. Okay, a path component is just the equivalence class of points under this. If that makes any sense. So, it's the equivalence class under the equivalence A is equivalent to B if there's a path between these points. If between A and B. It class of X, I should put that in there, of X under the equivalent relation A is equal to B, if there exists a path between A and B. Right. Okay. Now, is path connected? We say a space is path connected if there only exists one path component. Only one. So I do it like that, so it looks an L. Path component. And essentially, this is like saying there's a path between any q points in X. Right? If you think about it, it's literally just saying that every point is equivalent to every other point, right? Because that's what the path component is, right? And if there's only one, it means that every point is equal to every other point, and there exists a path between one point to every other point. Yeah. Or there exists a path between any q points if you really want to see it. The same thing. Simply path connected spaces. A simply path connected space is actually a fun one. Simply path connected. A space is simply path connected if you can continuously deform well, that's the name for a path, actually, is just a continuous deformation. This is another continuous deformation. If you can continuously form any one path into another path. right? Yeah. So we say a simply path connected space is one that has a map, or a map, if we will denote paths by P just for the sake of it. Yeah. So we'll do the unit interval, of course, by our first path. It maps to our second path, I'm pretty sure. I would hope so. Between any two paths, P1, P2, so that it's a 0, and then of course it's just the path. So 0, and of course P1 0 is equal to essentially just P2 0. P2 0, it should be at least. So now I'm looking because I forgot to look at the notes and I've completely forgotten. But this should be okay. Don't think I'll need. I don't necessarily need that. I don't particularly know what map I'm supposed to be doing, so let's just say I'm kind of. Made a mistake here. Actually, on add one thing, the endpoints have to be preserved, so that well, the endpoints are preserved. That's what. So this actually should be something closer to maps from 0, 1, the unit interval by the unit interval. I could just literally see the unit interval and to x, so that 0, 0 is equal to P1, 0, and 1, 1 equal to P2, 1, and all that fun stuff. So that's basically the rundown of path connectedness, simply path connectedness, normal connectedness, compactness, and all that fun stuff that we're gonna have to use later, and probably in the near future, because of what I want to do particularly is between topological manifolds or group theory and to run basic algebra, so we can go to basic understanding of algebraic topology. But I don't know. Honestly, I don't know. I just have to continue what I'm doing here with topology. Which the next lecture, let me think, there'll probably be on different types of topologies actually, which I don't know why it's today, but I just found this better to do earlier for some reason. And after that, know where we're gonna go. But at that point, I'll probably just, well, in the next lecture, I'll probably just discuss basic types of topological spaces, like product and quotient, all that stuff. Well, quotient spaces are probably gonna be less important, and homeomorphisms, because let's just say that they can be kind of important to understand homeomorphisms, you know. I mean, imaginably so. So, actually, probably also need to describe functions within topological spaces, which might be the next thing. Or, no, I'll just do topological spaces next. Either way, that's the end of this, and please like, comment, and subscribe. Give me suggestions or ask questions or correct me, honestly, doesn't be anything, because I'm doing this on the fly and have almost no idea what I'm talking about. Well, so thank you.